बिस्मिल्लाहिर्रहमानिर्रहीम रब्बिश शरह सदरी वयस्सिर ली अमरी वाहलुल उक़दतम मिन लिसानी यफ़क़हू क़ौली. Assalamu alaikum. Today we are going to do quantum mechanics by Mark Beck 1.2.4 Eigenvalues and Eigenvectors. The following is a mathematical problem that arises frequently, often as a result of a physical problem. We are given a matrix M bar and we want to find vector x and constants lambda that are solutions of the equation M bar x is equal to lambda x. In other words, there are some special vectors that when we multiply them by the matrix M bar give us back a scale version of themselves. The vectors that are solution to equation 1.43 are called eigenvectors of M bar and corresponding constants are called eigenvalues of M bar. If we multiply the matrix M bar with the vector x, we get back the same vector x and a constant lambda. Lambda is called the eigenvalue, x is the eigenvector, and this is known as the eigenvalue equation. How do we solve this problem? Start by rewriting equation 1.43 as M bar x minus lambda x is equal to 0. In order to factor out the vector x, we need to introduce the identity matrix 1 bar, which has ones on the diagonals and zeros everywhere else. In 3D, for example, the identity matrix is given by 1 bar is a 3 by 3 matrix with ones on the diagonal and zeros everywhere else. Another way to express the identity matrix is to say that its elements are equal to Kronecker delta lambda ij, which is defined as lambda ij is equal to 1 when I is equal to j and 0 when I is not equal to j. As we can see in identity matrix, delta 1 1 is equal to 1, delta 2 2 is equal to 1, delta 3 3 is equal to 1, delta 1 2 is equal to 0, delta 1 3 is equal to 0, and so on. The identity matrix is useful because multiplying it times any vector or matrix simply returns the same vector or matrix. For example, in 2D, multiplying 1 bar x is equal to, we'll have a 2 by 2 matrix in which delta 1 1 and delta 2 2 is equal to 1 and delta 1 2 is equal to 0, delta 2 1 is equal to 0. If we multiply it by the components of the vector x1 and x2, we get the same components x1 and x2 and therefore the same vector. Using this fact, we can insert the identity into equation 1.44 and obtain M bar x minus lambda x is equal to M bar x minus lambda 1 bar x. We have inserted identity into the equation. If we take out the vector x and we are left with in bracket M bar minus lambda 1 bar brackets close time vector x is equal to 0. M bar x minus lambda x is equal to M bar x minus lambda 1 bar x. 1 bar is an identity, we can introduce it because identity times vector gives the vector itself. If we take the vector x as common, we are in brackets left with M bar minus lambda 1 bar. M bar is a 2 by 2 matrix with components M11, M12, M21 and M22, whereas the identity is a matrix with 1 on the diagonals and 0 at off diagonals. If we multiply the identity with lambda and subtract it from the M matrix, we are left with M11 minus lambda, M12, M21, M22 minus lambda, vector x1, x2 is equal to 0. This is equivalent to a system of two equations, bracket M11 minus lambda bracket close times x1 plus M12 times x2 is equal to 0. The other equation is M21 times x1 plus bracket M22 minus lambda bracket close x2 is equal to 0. In three unknowns lambda x1 and x2, there is a solution to this problem if and only if the determinant of the matrix in equation 1.49 is 0. In 2 by 2 matrix, we find the determinant by multiplying the diagonal elements and subtracting it by the off-diagonal elements. Therefore, M11 minus lambda times M22 minus lambda minus M12 M21 must equal 0. We will just outline the rest of the procedure before doing a specific example. Begin by noticing that equation 1.51 is second order in lambda. This means that there are two solutions which we will call lambda A and lambda B. Once these eigenvalues have been found, each will have its own corresponding eigenvector xa or xb. To find the eigenvector, substitute the eigenvalue into the original equation, then solve for the corresponding eigenvector. When we find the determinant with the help of equation 1.51, we will get two values of lambda, lambda A and lambda B. Then we will substitute lambda A in equation 1.50 to get the eigenvector XA and lambda B into equation 1.50 to get the eigenvector XB. We will multiply the matrix M11 minus lambda A, M12, M21, M22 minus lambda A with a vector with components xa1 and xa2. Then we will find the two components xa1 and xa2, and hence we will get our eigenvector. This is equivalent to two linear equations in two unknowns xa1 and xa2. We can solve for them. We will carry out the multiplication of a matrix with the vector M11 minus lambda A times xa1 plus M12 times xa2 is equal to 0. The other equation is M21 times xa1 plus M22 minus lambda A times xa2 is equal to 0. In general, n-dimensional problems, there will be n eigenvalues and n eigenvectors. There is one last trick. The equation that determines the eigenvector, example equation 1.53, are not independent. The solution for the eigenvalues ensure that this is the case. This means that there is no unique solution to the problem. We can solve for xa2 in terms of xa1 or vice versa, but neither is uniquely determined. That this must be so seen in the fact that if xa is a solution to our original problem, equation 1.43, then any constant time xa is also a solution. There are an infinite number of xa's corresponding to lambda A. We are thus free to impose one more constraint in order to obtain a unique solution. Typically, we choose to normalize the eigenvectors. This means row xa1 conjugate xa2 conjugate times column xa1 xa2 is equal to mod xa1 square plus mod xa2 square is equal to 1. We find the eigenvalues by setting the determinant is equal to 0. Since this is a 2 by 2 matrix, it will give us two eigenvalues lambda A and lambda B. We can use the eigenvalue lambda A to find the eigenvector xa and the eigenvalue lambda B to find the eigenvector xb. If we substitute the eigenvalue lambda A into the equation 1.50, we obtain equation 1.52. From this we find that if we the components of the eigenvector are either in terms of xa1 or in terms of xa2, we do not have the unique solution of xa1 and xa2. To obtain the unique solution of xa1 and xa2, we will use the normalization condition xa1 square plus xa2 square is equal to 1. This constraint will allow us to calculate the exact value of xa1 and xa2 and hence our eigenvector. Thank you for watching. Allah Hafiz.